Good morning. Myself Mr. Jeet Singh. I am a student of Chemical Engineering Department of NIT Jalandhar. I am currently studying in the 4th semester. This video it's an assignment video on the topic of boiling and its regimes. Throughout this video we will be discussing many topics. We will be discussing the boiling process. We will be discussing the modes and or regimes of boiling, their subtypes. We will be discussing the boiling curve and many other topics. So starting with the process of boiling and its classic definition, boiling. Boiling is a process, it's a convective heat transfer process in which the phase changes from liquid to vapor. Boiling process is opposite to the process of the condensation. We know in the process of condensation, vapors condenses to form liquid. Now in the boiling process, the phase change is from liquid to vapor. The boiling process is used in many unit operations such as distillation, such as evaporation, or even in steam generation. Boiling process occurs when heat is transferred from the solid surface to the liquid in contact. What happens is, this is the solid surface and there is a liquid surface within it. Now heat is actually given to the solid surface. Then this solid surface transfers that heat to the liquid surface. This is actually happen in the process of boiling. The heat is transferred from the solid surface to the liquid surface that is in contact with the solid surface. Point of contact. Now in the boiling process, the surface temperature is maintained at a temperature which is higher than the saturation temperature. The term saturation temperature is actually referring to the boiling point of the liquid given. Obviously, if the temperature is greater than the boiling point, then and only then the boiling process will occur. Now the uses. Boiling is actually a process that has a wide application. Boiling process is used in boilers for steam formation. It is used in heat transfer in evaporators. It is used in drying foods or dehydration of foods. It has many applications. We will also know that in class 11 or 12 we have studied the process of distillation, that is also an application of boiling, which is separation of two liquids. So yes, experimentally there are many uses of boiling process. Now as we've discussed the boiling process, we will move on to the further topic. Now there is a thing that people think that phenomenon of evaporation and phenomenon of boiling, they both are similar, but that's not actually true. In both the processes, although liquid is transferring, the phase is changing from liquid to vapor, but both the processes are very different from each other, and that's what we are going to discuss now. That is differentiating between boiling and evaporation. Let's take a flask, both sides. Let's say it is a glass and both contains the liquid. Let's say the liquid in this flask is at 65 degrees Celsius and in this 100 degrees Celsius. Now I will start heating this. The temperature of the wall is TW and the temperature of the liquid is TSAT. Let us say that the liquid inside this flask is already at the saturation temperature, because we already discussed that boiling only occurs at a temperature that is greater than the saturation temperature. So for water, that is 100 degrees Celsius. Now let us start heating both the flasks. What we will see is in here the temperature will start rising, 65 to 66, 66 to 67 to 68. But what happens is the particles which are at surface the air will, when the airflow, what the airflow will do is blow away these particles with them. Even though the temperature is just 68 degrees Celsius or 69 degrees Celsius, this particle which was in the liquid form, it has already converted into the vapor form. So the first basic difference is evaporation can occur at any temperature, but the boiling it will only occur at the temperature when temperature is that temperature is greater than the saturation temperature. So that is the first difference. That now the second difference is that here we see the particle is removing from the liquid at the surface. So evaporation is a surface phenomenon, but boiling, it is a bulk phenomenon. Let's say there are these two particles. The heat is given to the solid surface. Now the heat is transferred from this to this. So the boiling process, it is occurring between even the layers of the liquid. So the second, now the third difference will come itself from the second point. That is, the evaporation occurs at a liquid vapor interface, and in boiling, the boiling occurs at solid liquid interface. Now the fourth difference will be bubble formation. In boiling, we will see the bubble formation, but in evaporation, there is no bubble formation. And what is the reason because of that? Because the particles which are getting evaporated, they are getting evaporated from the surface. But in boiling, these particles which are within the layers of the liquid, these particles evaporate in itself, and then the boiling occurs. So there is a bubble formation in boiling, but there is a no bubble formation in. And also in evaporation, the evaporation only occurs when vapor pressure is less than the saturation vapor pressure of the liquid. So this is what was differences between boiling and evaporation. So you can see that boiling and evaporation, these both the phenomena are actually really different from each other. Now, as we discussed boiling and evaporation, we will move on to the further topic, that is modes or regimes of boiling. Now, in this topic, we will be discussing pool boiling, flow boiling, or we can say forced convection boiling, saturation boiling, local boiling. So, we will start with the first one, that is pool boiling. Going by the definition, in pool boiling, we submerge the hot surface of the solid into the free surface of the large quantity stagnant liquid. Let us say we have a pot. The heat is given to the liquid which is present in the pot. Now, this heat, let us say this is at the temperature TW, this is at a temperature T saturation. Now, this heat will transfer to the particles that are just below or just in contact with the surface. These particles will get heated and acquire a temperature greater than the rest of the liquid's temperature. Now, what will happen is these particles will evaporate and convert into gaseous phase. Now we know that the density of gaseous phase is less than the density of the liquid. So what will happen is these particles will move upward, and we will see a bubble formation also. So these particles will move upward, and the liquid which was present on the upper layer, which is at a lower temperature, the temperature will be greater here and the temperature will be lower here, as we are providing the heat from the below. So TA greater than TB. Now these particles will move upwards, and the liquid which is present upward will move downward. So what happen will natural convection current will start generating. So the natural convection current will occur. Now this type of boiling is called pool boiling. Now in pool boiling there is no bulk fluid flow. The motion of particle is only because of the natural convection current is set up in the flask. There is no motion of the particles due to the bulk fluid flow. Let us say example of this will be a pot. We just set a pot in our kitchen and we are heating the water. This is a basic example of pool boiling. So I'm repeating again. The motion of particle is only because of the natural convection current is set up in the flask. That is not because of the bulk fluid flow. There is no bulk fluid flow in the pool boiling. Now, after this pool boiling, we will discuss the flow boiling, or as we can say, forced convection boiling. Now in flow boiling or forced convection boiling, what we see is like there is a pipe and the liquid is flowing through it, and there is some heating instrument which is providing the heat to the pipe. Now in forced boiling, the motion of the particle is due to an external mean like a pump or a motor. The motion of the particle is mainly due to bulk fluid flow. Now, this is the mean of forced convection. What happens is, a pretty cool example of forced boiling would be a chai wala making the chai. Let us say this is the pot he used for making the chai. What he do is, he needs to make the chai in large quantity because of his customers. So, what he do is, he keeps stirring the chai with a stirring instrument, thus providing forced or external mean for convection. Thus, the name forced convection boiling. And because of this, the chai will take less time to make, because it improves the rate of heat transfer, because the heat transfer coefficient is now increased. So this is forced convection boiling or flow boiling. In this, the motion of the particle is mainly due to the bulk fluid flow or an external mean. We provide an external mean for convection, like I've explained in this example, a chai wala making the chai. Now we will discuss the further part. Now the further part which we will discuss is subcooled boiling and saturated boiling. First we will discuss the subcooled boiling. By definition, subcooled boiling is the boiling in which the temperature of the stagnant liquid is lower than the saturation temperature. So what we have is, let us take a pot in which there is a liquid. Let us say the temperature of the wall, this liquid is, let us say, water. The temperature of wall is, let us say, 105 degrees Celsius. We are providing heat from this wall to the liquid, and let us say the temperature of the uppermost layer is 80 degrees Celsius. Now, the temperature of this liquid is actually lower than the saturation temperature. The saturation temperature for the water is 100 degrees Celsius. Now what will happen in subcooled boiling is, this wall will transfer the heat to the next the liquid layer that is in contact with this surface. So because of this, the liquid particle which are present at this layer, they will get converted into vapor because of the evaporation. So the bubbles will form, and these bubbles will start moving to the upper layers. As these bubbles move to the upper layer, the heat, the latent heat which is inside this bubble, because it is containing saturated vapor inside it, it will be transferred to the liquid which is above these layers. So the size of the bubble will start decreasing. So what we will see is the bubbles which are at the bottom layer are very big in size, and the bubbles which are at the upper layer are smaller, and thus they keep getting smaller and then they condense into liquid. So the upper layers of the liquid are actually getting heated by the latent heat of the bubbles, which is because of they are containing the vapors of saturation vapors. So this is how subcooled boiling is work. The explanation behind this is simply the heat is getting transferred to the bottom layer. Now at the bottom layer, boiling is occurring, because of which the bubbles are forming. So the bubbles which are formed are, let us say, have a radius r, but as these bubbles go upward in this container, they will get smaller and smaller, because the heat which is inside that bubble is transferred to the liquid for the above layers, and this is how the above layers are getting heated, and thus the bubble condensed into the liquid. So this is how subcooled boiling is working. Now we will see the next part. Now the next part is saturated boiling. Saturated boiling is also a type of pool boiling. What happens here is, in saturated boiling, let us say we again take a pot and there is liquid in this pot. In saturation boiling, the temperature of the liquid is equal to the saturation temperature or a little bit greater than that. So we have temperature of liquid is equal to the saturation temperature. So let us say this is water. So the T saturation will be equal to 100 degree Celsius. So we are giving heat to this pot, and there are bubble formation throughout the liquid everywhere. Bubbles are forming everywhere, in the below layers, in the above layers. So we know every particle in this liquid is at a temperature that is T saturation. Now what will happen is, as we are giving heat to the surface, the bubbles are getting bigger and bigger. So as the bubbles move from lower layers to the upper layers, the size of bubble will get larger and larger and larger. So what happens at the top more layer is, the bubble gets unstable and thus collapses. So this is how bubbles are diminishing in this process. So that is the reason behind this, because of which bubbles are disappearing. So in explanation, the temperature in saturation boiling is equal to the liquid temperature is equal to the saturation temperature. Bubbles are forming at the bottom layer of the liquid and thus going to the higher layers. But as the temperature throughout the liquid is same, the bubbles are getting bigger and bigger and thus getting unstable, and they collapse at the uppermost layer. So this is saturated boiling. Now the next topic which we will discuss is pool boiling curve. It is a very important topic. This curve is really important. This curve is actually the graph between excess temperature and heat which is transferring from the wall to the liquid. So on the x-axis here we are taking excess temperature. Now TXS. What is actually the excess temperature? It is nothing but the difference between the temperature of liquid minus saturation temperature. Now let us say water. So this excess temperature, let us say the water is at 30 degrees Celsius. So and the saturation temperature of water we will know is 100 degrees Celsius. So at that point the excess temperature of the liquid will be 30 minus 100, that is minus 70 degrees Celsius. But here we are pointing the in degrees Celsius, this is in degrees Celsius, we are pointing the curve in positive. So this means the T liquid is greater than the T saturation. So this curve will be explain where the temperature of the liquid is greater than the saturation temperature. So it will be greater than 100 degrees Celsius. So what happen will, we will study it alongside with the flask. Let us say this is a flask and it is getting heated by a burner. This is a burner. Okay, it is on a stand. This is a burner. It is getting heated by a burner and there is liquid in this flask. First, when this burner or the heat will heat this surface, which is wall, let's say the temperature of the wall is TW, this wall will transfer the heat to the layer which is next to this wall. Let us say there are particles, liquid particles here. So what will happen is the heat will be transferred from this wall to these particles, and what will happen will these particle will the temperature of these particle will rise. Now these particles, as their temperature is rising, they are evaporating, they are converting into vapors and they are having greater heat in them. Their saturation vapors, they will rise above. Why? The explanation is, as they are converting into saturation vapor, the density of the bubbles is now less than the density of the upper layers. So their weight will be decreasing. Now their weight, as their weight is decreasing, the liquid which is above or the layer which has more weight than this, that will come to the bottom and this will go above. So this curve is something like this in the beginning. So what will happen is, from let this point is O and this point is A. So what will happen at OA is, just it is the process OA is free convection boiling. Which we have discussed here. The particles are rising and the layer which has more weight, it is coming downward. So a free convection current sets in. So this process is on the curve is related by OA. So basically the particles are going up because of the saturated vapor. They have less density and they are going up. The more the layer with the more weight is coming down. So this is how a convectional current sets up, and this will goes on and on and on. Now from A to point B, what happens from A to point B is these bubbles are forming. Now at this point these bubbles are larger in size, but as they go above, they will transfer the heat which is inside them, the saturation vapor heat. They will transfer that heat to the liquid that is above them, and that liquid will get heated. Now as the liquid will get heated, the bubble they will get less heated, and the bubbles, their size starts decreasing, and thus they collapse because they have already transferred their heat to the above layers. So what we see is in A to B part, bubbles are forming, but because of the convectional current and the layers above them has a lower temperature, they are getting destroyed before they reach this top layer. They are not reaching at the top layer, they are getting destroyed even much before that. So now from B to C part, in B to C part, what we will see is as the burner is giving heat to this layer, and this will heat the particles above layer, and that will heat the particles above there, natural convection current is getting heated, and more bubbles are forming. So in B to C part, what will happen is more and more bubbles will form, and there will be a bubble flow in this region, and in this part bubble will reach the upper layer. So B to C part is nothing but it is denoting that the bubbles which are generating at the bottom because of the heat given, they are reaching at the top layer. So this. Now A to B to C, this process is called nucleate boiling. Nucleate boiling. Now at C point, there will be maximum heat flux, because at this point bubbles are forming a flow and they are going upward to the uppermost layer. So we can label AB part as bubble collapses. Why? Because they didn't have the much heat energy to go to the above layer, because the heat energy they had is they transferred to the upper layer which has a lower temperature than that. And from D to C, bubble flow occurred. Now what happened after C is, let me label the heat first. On y-axis we have heat. Now this heat is the heat transferred by the solid surface to the liquid surface, by the unit solid surface to the liquid. So it will be in watt per meter square, as we are taking the unit solid surface. So on y-axis we have the heat transferred through the unit solid surface to the liquid, and on x-axis we have Txs. Also the heat transfer can be given by Q is equal to H T liquid TW minus T saturation. Now here the TW minus T saturation is same as the we are taking here. It is also can be written by as H delta TE, and delta TE is Txs. Txs also denoted as delta TE. So coming back on the full boiling, here from C to D the curve will look like this. Now what happens at C to D? Actually, as we discussed before, from A to B, from O to A, free convection boiling, heat is transferring to the liquid. There are bubbles forming and they are giving that heat to the liquid and thus collapsing, bubble collapse. And from B to C, what happen will the more and more heat will be transferred and there will be a bubble flow. Now from C to D, as there is more and more heat is transferring from the surface to the liquid. So what happen will, when this bubble reach the outermost layer, what happen? These small bubbles, 2 or 3 bubbles, these will merge together and form a bigger bubble. Now, force of buoyancy, we know the gravitational force accountable. These bubbles, when merged together, their weight increases and so does their size. Now, these bubbles will start coming downward and these bubbles will settle at the bottom. Now, these bubbles are very large in size. The more and more heat is giving, the more and more small bubbles are merging together. They are gaining the weight, and now because of that weight, they are coming down at the bottom. But how does this explain the decline in the from C to D? Now, as we see, these bubbles are coming down and getting settled on the bottom. So what they do is they make a film-like structure. So they are making this structure, this film. So now this film, it is acting as a thermal resistance body. They will collapse together and they will form a pocket. And because of this pocket, there will be, the burner is transferring the heat to the solid surface. Now the solid surface, the work of solid surface is to transfer the heat to the liquid. But as we see, there are bubbles at the bottom. So because of these bubbles, the heat will be not transferred to the liquid and there will be thermal resistance. Because of this thermal resistance, the heat transfer will come lower and lower and lower, and thus from C to D, the heat transfer declines. So from C to D, the heat transfer declines, and this state is known as transition boiling. So from C to D, this curve is known as transition boiling. So in transition boiling, a vapor pocket is occurring at the bottom, and that pocket is behaving as a thermal resistant body. Now because of this thermal resistance, the heat will be not transferred from the burner to the liquid, so the heat transfer declines. So as we see from 30 to 120 degrees Celsius, what happens is the curve declines. Now after C to D, the curve looks something like this. We have discussed that there is thermal resistance and the curve is declining. So now why does the curve go up? And you can look at that the E point is above the C. What happened? So that this curve is going instantaneously upward. So actually, as this process continues, more and more bubbles are coming down. So there is a very large quantity of bubbles, or I can say vapors, coming at the bottom. Now, as they will come at the bottom, layer by layer, they will form a very large body. Now, this large body is a vapor pocket. This large body is a vapor pocket. Now, this vapor pocket will transfer the heat which is burner giving to the solid surface to the liquid by radiation, because this film is produced. Now this film is transferring that heat, because look at this, the temperature is increasing, the temperature difference is increasing. So as delta T is increasing by a very large value, there will be heat transfer, obviously. So this film become unstable, and thus this film gave up, and this film, the situation very unstable here, and that is why this is transferring the heat through radiation. And as we know, in radiation, the heat is proportional to T raised to power 4, temperature raised to power 4. So that is the reason that this curve is going readily upwards. So this is how from the curve from D to E is behaving, and the D to E curve is called film boiling. So this was the pool boiling curve. From O to A, we discussed with the curve, there will be a small amount of bubbles that will form at the bottom layer, and they will rise above. They will heat the upper layers and they will distort. Now from A to B, the bubble collapses. But as the heat is getting more and more, the more and more bubbles will be formed and there will be a bubble flow. Now the bubble flow is upward from B to C. What happened upward is from C to D, the bubbles, all the bubbles which are smaller, they merge together and they form heavy bubbles. Because of their weight, they are settled down at the bottom, and so does the curve decline. Curve decline because why? Because when those bubbles settle down at the bottom, they will behave like a thermal resistance body. So because of that thermal resistance, the heat from the burner will not go up to the liquid, and so does the curve declines. After that, those films collapses together to form a vapor pocket. Now that vapor pocket will transfer the heat as a radiation. So now there is radiation, and we know in radiation the heat is proportional to T raised to power 4, and because of that the curve is readily going upward. So this is how the pool boiling curve works. On x-axis we take excess temperature, on y-axis we take heat transferred by the solid surface to the per unit solid surface to the liquid. So this was the pool boiling curve. The next topic which we will discuss is nucleate pool boiling. In nucleate pool boiling, heat flux increases due to rapid increase in excess temperature. So the heat flux in nucleate pool boiling increases because there is an increase in excess temperature. Now in this region, the range of temperature is generally from 5 to 30 degrees Celsius. So what happens in nucleate boiling is the bubbles start forming, but those bubbles does not reach up to the layer because that energy they have, the heat energy they gave to the above layers. So bubbles start forming and they started going upward, but as soon as they start going upward, they give their energy to the upper layers. They will get heated, the layer's temperature will rise, but the bubble will collapse. So now after that, as that excess temperature increases, what we see is there is a lot of bubble formation. There are the number of bubbles which started forming is a great number. This region, this point is also called isolated nucleate boiling. So now what will happen next is those bubbles will form a bubble flow, and they will reach the upper layer of the liquid. So after that, factors affecting nucleate boiling. Now there are many factors which affect boiling. The factors which are affecting nucleate boilings are as follows. The first factor is material. The material of the solid. In specification, in which we will see is that, like, if the material of the solid is highly finished, then the heat transfer will be low, because the second point, which is roughness, is also a factor which affects the nucleate pool boiling. Now what happens is, if the surface of the pot is rough, the heat transfer is generally more, because the liquid which is in contact with the surface, the particles, as just say this is the rough surface. Now as the surface is rough, there is more surface area for the liquid particles to be in contact with, as instead of a plain surface, there will be a small number of particles which will be in contact. So as roughness increases, heat transfer also increases. So after that, the third factor will be liquid properties. Now, how liquid properties affect the heat transfer? Let's say viscosity. As the viscosity of the liquid increases, the bubble size increases. Now, if the bubble size increases, bubble growth will decrease, because as the size of bubble increases, it becomes unstable and it pops out. So, the bubble formation or bubble growth will decrease, and so does the heat transfer will decrease. So, in this, let's say viscosity increases, which bubble size will increase. As bubble size will increase, bubble growth will decrease, and so does the heat transfer will decrease. So this fourth factor we can say is agitation. Now agitation, we can say there is a pot in a microwave. There is a pot we placed in microwave. Now the pot is rotating, because of which the liquid is also this is providing an external convection to the liquid, because of which heat transfer will increase. So agitation does nothing but provide forced convection to the liquid. The last part is pressure. If we increase the pressure, the heat transfer or heat flux will increase, but only up to a certain point, that is the critical flux point. After critical flux point, there is no role of pressure. Pressure cannot affect the nucleate cool boiling. So these were the points or the factors affecting nucleate cool boiling. Now the next topic is bubble growth. So how does bubble growth is affected? Simply we will take surface tension. We can also say this is also another factor that affects nucleate cool boiling. How the surface tension works? Let's say we have three cases. First case is in which surface tension is very low. Second case in which surface tension is partial, and a third case in which there is a very highly surface tension is there in the liquid. Now what will happen is, let's say this angle is alpha. When the surface tension is low, the surface tension will go, there will be an oval shape of the bubble. There will be an oval shape of the bubble. So basically surface tension is the capacity of wettability. We can say it is the capacity of wettability. How wet a liquid can get, that is the surface tension. Okay, so now capacity of wettability. As surface tension is high, liquid is very wettable, and as surface tension is low, liquid is very wettable, and so the bubble will form a oval shape. Now as surface tension increases, the wettability decreases. So let's say this is partial wettable. This is partial wettable. So in this case, the bubble will not form accordingly. There will be not a quite shape of bubble as compared to the first one. Now in third, let's say surface tension is very high. So this is not at all wettable. In this case, bubble formation will be impossible. So the only tension where the only case where the surface tension is low and wettability is good, the bubble form will be oval, and it will be quite easy for this bubble to leave this surface and go above and leave the surface. So what happen is, this bubble generally boil, go to the upper layer of the surface, form slug of vapor and thus leave the surface. So this was the part of bubble growth. The next topic which we are going to discuss is transition boiling or unstable film boiling. As we know that nucleating boiling flux cannot increase indefinitely. So when nucleating boiling flux reach at its maximum value, we call it critical flux. So after that, vapor will form a film at the bottom of the surface and thus the heat transfer start distorting and the heat transfer rate decreases. Now the transition from nucleate boiling phase to the film boiling phase is known as boiling crisis. So boiling crisis is simply now in this process or in this region, boiling crisis region, now in this region or the boiling crisis region, the process is very unstable because there is a film that is being formed at the bottom of the surface. Now this film is actually stopping the heat from going to the liquid. This film is acting as a thermal insulation. This film is acting as a thermal insulation. Because of this, the process becomes highly unstable and thus the boiling crisis, the term boiling crisis. Now, if the flux decreases to the D point where it is called the minimum heat flux or the minimum flux, this point is also called as Leidenfrost point. At this point, if the flux is further decreasing, it will not be continued in the same manner. The nucleate boiling will start again. But after the Leidenfrost points, the film becomes unstable and there is a vapor pocket formed. Now this vapor pocket acts as a body itself. Now this vapor pocket acts as a body itself and thus transfer the heat which is coming to the surface from this to the liquid part by radiation process. So here the heat is transferring by the process of radiation to the liquid which is above this pocket. And this regime is also called film boiling or stable boiling. So this was the last part which we were going to discuss. This was film boiling or we can say the stable boiling. So one more effect which is come from the Leidenfrost, it is Leidenfrost effect. What is this effect? This effect is generally when liquid which has a lower temperature, lower saturation temperature than the metal which it is in contact with, which is at a very high temperature, that liquid is actually forming a vapor film just because it wants to protect the vigorous or the rigid boiling. Vigorous or rigid boiling, when the liquid forms vapor pocket to decrease the boiling process or to decrease the intense of vigorous boiling, this effect is also called as Leidenfrost effect. So this was all about boiling. Throughout this video we have discussed boiling, different regimes, pool boiling curve, types of pool boiling, and then at last transition boiling and unstable boiling. Thank you very much.